Thanks for tuning in. This is my reproduction of rapid learning or feature reuse towards understanding the effectiveness of Mammal. I'm going to start with a little bit of background, explain to you what Model-Agnostic Meta-Learning is, and close with the results of the study and of my own reproduction. Starting with the background. Meta-learning, that is learning to learn, improving parts of the optimization strategy of a model rather than its parameters directly. The application of our study is few-shot learning. We want strong fine-tuning capabilities to new tasks from only a few samples. The architecture of the study is an image classification architecture with 4 convolutional blocks and a fully connected linear classifier that is often called the network head. Model-agnostic meta-learning, or Mammal for short, is all about finding a good starting point for fine-tuning. This starting point are the initial parameters of our model. We then update this parameter via gradient descent, and the corresponding loss is simply the sum of the per-task losses of the fine-tuned models. Now, if we repeat this iteratively, sampling more and more tasks, theta will eventually converge to a starting point that is allowing good fine-tuning for tasks on average. Because of this, even for a few shots, this method can be applied very successfully, given that we can sample enough tasks. Vinyals et al. Conducted a study on the fine-tuning behavior of mammal models. In particular, they compared the feature similarity before and after fine-tuning and figured out something very interesting. As it turns out, on a very popular few-shot learning benchmark for image classification, only the head of the network is truly adapting, with the other convolutional layers barely showing any adaptation during fine-tuning. As a result, they come up with a method called Anil, which is a slight modification to Mammal, where we're only fine-tuning and meta-learning the fully connected head, simply pre-training the convolutional layers and not subjecting them to any meta-training. Thereby, we are hoping for general features in the convolutional layer that we can reuse. The reasoning is as follows. Don't fine-tune the network body, so the convolutional blocks, because meta-learning is just too expensive for so little adaptation. On the other hand, the head is very important for assigning the features then to classes, which can vary wildly among tasks. As a result, Anil can be thought of Mammal plus efficient feature reuse. The efficiency of this we can study when comparing Anil to Mammal. Here I've compared it to a less computationally expensive version of Mammal called faux Mammal, which is its first-order approximation. However, it is known to behave similarly to Mammal and have the same test performance on the given benchmark. For comparison, I also included results from the first-order approximation to Anil. When we look at the loss and accuracy curves during training, we see that all of the methods behave fairly similarly throughout the training. And also their test accuracy is almost the same, with Anil having a slight edge over Mammal. And this all while being almost 3 times faster during testing and 1.2 times faster during training. This was a fairly short introduction, so if you want to know more, I recommend checking out the original paper. There's also a lot more to learn about meta-learning and Mammal in particular. And I want to also mention something about a recent work suggesting that perhaps the benchmark that Vinyals et al. Used is simply too homogeneous, thereby making general features easier exploitable, and that it's not showing the true capabilities of Mammal.